You see, till now we did these topics in the chapter moving charges in magnetic field. Okay.
Yes, sir.
Uh, First, current carrying conductor produces magnetic field. And around a conductor there is a magnetic field. Current can create different effects. Due to current there is a heating effect. Due to current there is a magnetic field. Understood?
Yes, sir.
And due to current there is a chemical effect also, electrolysis. So current can create different effects. In the present chapter we talk about magnetic field produced by current carrying conductor, and unit of magnetic field is a Tesla. Unit of,
Yes.
and you can write Tesla also as Newton per ampere meter. Newton per ampere meter. And around a conductor, suppose in the diagrams you have shown two straight conductor. If current is going upward in a straight conductor, around the straight conductor magnetic field is produced. Magnetic lines are concentric circles around a straight conductor. And if current is going upward direction, then magnetic lines around the conductor is in anti-clockwise direction. If current is going in a downward direction in a straight conductor, then magnetic lines are in clockwise direction. And if you want magnetic field at any point, then you have to draw tangent at that point on the circle. If you draw tangent at any point, that gives direction of magnetic field at that point. Are you following? If you want magnetic field at any point, if you want magnetic field at any point, you have to draw tangent. Suppose I want magnetic field here, I have to draw tangent. This tangent will give direction of B bar. If I want magnetic field here, I have to draw tangent there. That tangent will give direction of magnetic field. Oh, sorry, not like this. You have to draw tangent in the direction of line. In the direction of line. This is the line. Yes, you have to draw line in the direction. So you have to draw tangent in the direction. The tangent here is in this direction. Tangent. This is B bar. And here if you draw tangent to the circle, that tangent will give direction of magnetic field. Is it? Here it is a direction of magnetic field along this side. Here it is along this side. And how do you get direction of magnetic field? Direction of magnetic field is along the tangent drawn to the magnetic line at that point.
Yes, sir.
Okay. So and also next you see next we did how to find the direction of magnetic field around a current carrying conductor. The direction of magnetic field is you can find by right hand palm rule, and you have to keep right hand thumb in the direction of right hand thumb in the direction of current. Then the fingers, the right hand palm fingers, if you fold the fingers, the way the fingers are folding, that gives direction of magnetic lines. If you want magnetic field at this point, you have to draw tangent there. You have to draw tangent at that point. You have to draw tangent at that point. So at this place, the magnetic field is along this side, along the tangent B bar. All right. And what is the force on a current carrying conductor? Force on a charged particle moving through magnetic field. Force F is equal to Q into V bar cross B bar, where V is velocity of the particle. V is the velocity of the particle. V velocity of particle. Velocity of the charged particle. It is already written. Q is the charge of the particle, and theta is the angle between velocity of the particle and magnetic field. So F is equal to Q V B sin theta, and in vector form F bar is equal to Q into V bar cross B bar, and the direction of this force is perpendicular to the plane containing B and B. Cross product rule. You can decide direction of force by right-handed screw rule. Right-handed screw rule. Okay, you can find, yes, yeah, this one. After this, if after this you say, now F is equal to QVB sin theta. Based on this equation, you get 1 mark questions in CBSE exam. F is equal to QVB sin theta. If theta 90 degrees, sin 90 1. So maximum value of sin theta is 1. That is when theta is 90. Therefore, the charged particle experiences maximum force when the particle is moving at 90 degrees to direction of V bar. If theta 0 degrees or 180 degrees, and if a charged particle moving parallel to magnetic field or it is moving opposite direction to magnetic field, in either case force is 0. The charged particle do not experience any force when it is moving parallel or anti-parallel to magnetic field. Direction of force can be decided by using cross product rule, right hand screw rule, or you can decide by Fleming's left hand rule. Fleming's left hand rule. Okay. Do you know Fleming's left hand rule?
Yes, sir.
What is Fleming's left hand rule?
So if
Left hand's thumb. Left hand's thumb is in the direction of,
the force
yeah,
index finger is in the direction of magnetic field.
yeah, left
Middle finger is in the direction of um,
left hand index finger is in which direction? Along magnetic field.
magnetic field. Sir.
Index finger along magnetic field. Middle finger along,
Velocity of the
yeah,
particle.
middle finger along velocity of the positive charge. Middle finger along velocity of the particle along V bar. V bar of positive charge. V bar of positive charge. And then thumb will give direction of force. Then thumb will give direction of force. So this is next. We did we have shown direction of force. You see, I have shown one surface of a table. On the table surface, there is V bar and B bar in the plane of the table. V bar and B bar are in one plane. What is that plane in the diagram? It is the surface of the table. Then, if you rotate cross product V bar cross B, if you rotate a screw from V to B, screw will go up. If we change the direction of V bar and B bar, then if you rotate the screw in the second figure, if you rotate the screw from V to B, then screw will go down. Otherwise, you can rotate right hand palm. Right hand palm, if you rotate from B to B, then thumb will come upward. Understood?
Yes, sir.
V bar cross B bar. Otherwise, you can apply like this also. Fleming's left hand rule also you can apply and you can check. And V bar. V bar you keep in the direction of middle finger, B bar in the direction of index finger, then thumb will come upward in the first figure. In the second figure, thumb will come downward direction. Is it?
Yes, sir.
Then, after that, we did the same thing you can express in terms of IJK. IJK. They ask 1 mark question, sir. IJK. You see one figure I've shown. V bar is along I cap. V bar is along x axis, sir. V bar is along y axis, sir. Then F bar will come along negative z axis. Then after this, we did one problem. An electron is moving along west. An electron is moving along west. Electron moving along west means you have to take V bar towards east. Direction of V bar you have to take in the direction of velocity of positive charge. In this diagram, electron is going towards west. Electron is moving towards west means you have to take V bar towards east. Then magnetic field is along north. Then what is the direction of force? What is the direction of force on electron? If you apply Fleming's left-hand rule, the force thumb will come in the direction of upward direction.
Yes, sir.
So, what is the direction of force on electron? What is the answer? Direction of force is in upward direction. Answer: direction of force on electron. Direction of force on electron is in vertically up. Is vertically upward direction. Right?
Yes, sir.
Then we did a magnetic field is represented by drawing some symbols. If we draw cross marks into marks, that means magnetic field into the plane of paper. If we draw dots on a paper, dots indicates magnetic field out of plane of paper. And also when a charged particle enters into magnetic field such that velocity is perpendicular to b1, then the particle will follow circular path. Very important this point. You get many questions in CBSE examination on this concept. When a charged particle enters into a magnetic field such that velocity is perpendicular to b bar, then the particle will follow circular path. Then what is the radius of that circular path? Radius of that circular path is mv by qb. How it is mv by qb? They ask derivation. Force on the charged particle is qvb. Force is equal to qvb. This force acts like a centripetal force, mv square by r. From there you get r is equal to mv by qb. Then time period of the particle. Time period means the time taken by the particle to complete one revolution in the circular path. How do you get time taken? Time is equal to distance by speed. Distance traveled is 2 pi r. Speed is v. So 2 pi r by v. But r place में you have to write mv by qb. In place of r you can write mv by qb. From there you will get 2 pi m by qb. And that time period means the time taken by the particle to complete one circular path, 2 pi m by qb. And frequency of the particle. Frequency of the particle means number of revolutions made by the particle, that is reciprocal of time period. Nu, frequency nu is equal to 1 by t. From there you get nu is equal to qv by 2 pi m. And here one important point, time period does not depend upon speed of particle. Time period does not depend on speed of the particle. And radius of the particle, radius of the circular path is directly proportional to velocity of the particle. More the velocity with which it enters in the field, more the radius it follows. Then we did about force on a current carrying conductor in magnetic field. Force
Yes,
on
sir.
a current carrying conductor in magnet. This is also little somewhat important. Force on a current carrying conductor. The force formula is equal to F is equal to ILB sin theta. In vector form, F bar is equal to I into L bar cross B bar. L bar ante length. L bar direction is along the direction of current. Force on a current carrying conductor. This derivation is important. F is equal to ILB sin theta. You get numerical problems on this equation. F is equal to ILB sin theta. Then Ampere circuit law we did. What is Ampere circuit law? Line integral of magnetic field around a closed path is equal to mu naught times current enclosed by the path.
Yes, sir.
So integration of B bar dot DL bar around a closed path equal to mu naught I. Is it okay?
Yes, sir.
Integration of BDL cos theta is equal to mu naught I. Integration means you have to take a summation of BDL cos theta around the path.
Yes, sir.
Where theta is the angle between B bar and DL bar. Theta is the angle between B bar and DL bar. What is I here? I is the current enclosed by the path. I is the current enclosed by the path. Then, using Ampere circuit law, we have derived expression for magnetic field due to infinite long straight current carrying conductor. Using Ampere circuit law, derive expression for magnetic field due to an infinite long straight current carrying conductor. This we get important derivation. E- Based on final this equation, you get questions. What is the magnetic field at a distance r from a straight conductor? B is equal to mu naught I by 2 pi r. What is the magnetic field at a distance r? Mu naught I by
Mu naught I by 2 pi r.
mu naught I by 2 pi r. Okay.
Yes, sir.
Then there are some questions we did. Suppose if current is going in same direction both conductors, there are two parallel conductors M and N, and in the conductors I1 and I2 are the currents passing through the conductors. We have taken one point P between the two conductors. That point P is at a distance d1 from M and d2 from conductor N. What is the net magnetic field at P? Due to M, due to M, the magnetic field is into the plane. Due to M, the magnetic field is into the plane. Due to M. Due to N, the magnetic field is out of the plane. Due to N, the magnetic field is out of the plane. Okay, so therefore, what is the net magnetic field? Net magnetic field is Bm minus Bn. One, due to conductor M, magnetic field into the board. Due to N, the magnetic field is away from the board. So net magnetic field is Bm minus Bn.
Yes, sir.
Then, then we did force between two. Very important derivation. Very important. This is very important derivation. Force between two infinite long parallel current carrying conductors. There are two conductors shown here, conductor X and conductor Y.
Yes,
Currents
sir.
are I1 and I2. The two conductors are separated by distance d. Now when current is passing through them, they create magnetic field around us. And a conductor X create magnetic field. Now Y conductor is in the field of X. Similarly, conductor Y also creates magnetic field. Now conductor X is in the magnetic field of Y. So they
Yes, sir.
interact each other. The two conductors they create magnetic field, and the magnetic field they interact. Due to that interaction, they exert force on each other. Force on conductor X, force on conductor Y. How do you get force formula? You have to apply formula F is equal to ILB sin theta. Based on that, you will get the formula force on conductor Y is equal to mu naught I1 I2 L by 2 pi d. Similarly, conductor on X also the same force. అంటే the two conductors they exert equal and opposite forces. If current is in same direction in two conductors, they attract each other. If current is in same direction, the two conductors attract each other. Okay, what is the finally formula?
F is equal to mu naught I1 I2 L by 2 pi d.
Yes, this is the force per L length. If you want force per unit length of conductors, if you want per force per unit length of conductors, force per unit length of conductors, force per unit length of conductor అంటే F by L. F by L is equal to mu naught I1 I2 by 2 pi d. This is the formula for force per unit length. Force per unit length of conductor. Then, okay, force per unit length of conductors. Mu naught I1 I2 L by 2 pi d. Alright.
Yes, sir.
Next, based on this force per unit length, force per unit length, based on force per unit length, we get define 1 ampere of current. This is also important definition. Define 1 ampere of current based on the force between two parallel conductors. Force per unit length is 2 into 10 power minus 7 Newton per meter. So 1 ampere is that current. 1 ampere is that current which when maintained in two parallel infinite long conductors separated by distance of 1 meter in vacuum, they exert a force of 2 into 10 power minus 7 Newton per meter on each other. Okay.
Yes, sir.
Then after this, yes, this is force between two parallel conductors. Then force per unit length. Based on this, we define 1 ampere of current. After this, we did Biot-Savart law. Biot-Savart law. What is Biot-Savart law? To find magnetic field created by a small element of a current carrying conductor. There is one element dl. Through the element dl, some current I is passing. Due to the dl element, what is the magnetic field at a distance r from the element? The magnetic field dB proportional to ideal sine theta by r square. From there you get dB is equal to mu naught by 4 pi ideal sine theta by r square. And the direction of B bar. Here the direction of magnetic field is perpendicular to the plane containing dl bar and r bar. This you can decide by using your right hand palm rule. You have to keep a thumb in the direction of current and your fingers, thumb in the direction of current and the fingers, the palm finger should be in the direction of R bar. Then if you fold the fingers at that place, whatever direction you can fold, the direction of in which the fingers fold, that is direction of magnetic field.
Yes, sir.
So on the right side of this dl element, magnetic field into the board. If we take a point on the left side of the conductor, magnetic field is away from the board. I hope you are following. Next, you see here, if some cases have shown, and also you should know what is the value of mu naught. Value of mu naught is 4 pi into 10 to the power of minus 7 Tesla meter by ampere. Mu naught is
Yes, sir.
called permeability of vacuum. Permeability of vacuum means we are assuming that there is a vacuum around the conductor. If some other medium is there around the conductor, then you have to write permeability of that medium. Ah, if current is going up, right side magnetic will into the board, left side is away from the board. Okay, you should
Yes,
know
sir.
you should know how to decide the direction of magnetic field around a conductor. Then we did using Biot-Savart law. We derived expression for magnetic field at a point on the axis of a circular current carrying loop. We have taken one loop, and on the loop we have taken one point P, one point on the loop at a distance x. We have taken a point at a distance x from the loop. Suppose that point is a P. P is a point on the loop at a distance x. P is a point on the loop at a distance x from the loop. At P, due to one element dl, there is a magnetic field dB. The dB you have to divide into two components, dB sin phi, dB cos phi. Similarly, you take another element diametrically opposite to the first element. Due to another dl also, there is a magnetic field dB. The dBs you have to resolve into two components, dB cos phi, dB sin phi. Cos phi components get cancel out, whereas dB sin phi are in same direction. So like this, due to every element you get one dB sin phi. And the total magnetic field is integration of dB sin phi. Here dB is mu naught by 4 pi ideal, and by Biot-Savart law mu naught by 4 pi ideal sin theta by root of r square plus x square whole square. Here theta 90 degrees, because dl bar makes 90 degrees with the line.
Yes, sir.
From there you will get, and also from figure sin phi is equal to r by root of r square plus x square. And in the integration second equation dB sin phi, you have to substitute dB and sin phi. If you substitute 1 and 3 in 2, you will get finally the formula mu naught I r square by 2 into r square plus x square power 3 by 2. Okay, what is the magnetic field on the axis formula? What is the magnetic field at a point on the axis?
B is equal to mu naught I r square by 2 r square plus x square whole to the power of 3 by 2.
3 by 2. If there are n number of turns in the coil, suppose there are n
Mu naught
number. then it is mu naught Ni r square by 2 into r square plus x square power 3 by 2. If you want
Yes.
magnetic field at the center of the coil,
Mu naught Ni by 2r.
yes, very important. And also in the right side I have shown two diagrams. If direction of this is a coil, this is a loop, this is a loop. In the loop, if direction of current is anti-clockwise, then magnetic field is away from the loop. If direction of current is clockwise, then magnetic field is towards the center of the loop. And you can decide by using again your right hand. You fold the fingers in the direction of current, then thumb will give direction of magnetic field. Your right hand thumb, fold the fingers in the direction of current. If you fold the fingers in the direction of current, then thumb will give direction of magnetic field. This we did. And then we did magnetic moment of a coil. Magnetic moment of a coil M is equal to NIA. Very important relation this is. This is very
Yes.
important relation. I put a star marks here. That means so important. Magnetic moment of a coil M is equal to NIA.